In this recording, we're going to take our SPSS output and put it into Excel, and then look at some of the things that we have to manually calculate. We have to manually calculate confidence interval, effect size, draw some publishable graphs, and do some other calculations in order to do all that. So let's get started and look at our Excel spreadsheet that uses the longitudinal vision data and looks at spherical equivalence, peripheral refraction, and relative peripheral refraction. So when we did our mixed model, we looked at a one-way analysis of variance. We had init years, and we had relative peripheral refraction, spherical equivalence, and peripheral refraction. And then we copied and pasted from the output the estimates. These are the years, the mean estimates given for each of the years. We had the section on covariance parameters, the main effects, the test, the init years with the p-value, and the paired comparisons. And I just copied this for each of the three. We used syntax to easily put out three different tests of three different dependent variables. And so from that, we've made a graph. The bar graph is looking at by year, the mean relative peripheral refraction. And you can see the relative peripheral refraction starts at a myopic refraction and goes to hyperopic refraction, relative hyperopic. So this is relative. This is spherical equivalence, or it's peripheral spherical equivalence minus spherical equivalence. So it looks like that. Before it, this is init years and this is year 0. It kind of shifts 1 year prior, but it's going up, and then it pops up, and then it kind of looks like it's drifting down. I don't think it goes all the way down to the bottom, but then I don't really know either. So that's what this group did. When we're talking spherical equivalence, it's kind of interesting. We start out myopes. These are myope only. They start out hyperopic, and they go down, 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 down. And this is relative peripheral, or this is peripheral refraction. Now, I find this pretty interesting because they start out in the periphery, hyperopic, and then they go down, 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 down. So these are all myopic spherical, peripheral spherical equivalence. Here they all are on the same chart. So you can see spherical equivalence is going down, kind of drops off that cliff right there and goes down. Peripheral refraction is kind of smoother, and it crosses. So that year 1 minus 1 year before is actually less. It's relatively lower. When you subtract them, you get this hyperopic defocus at 1 year, and it comes up and it stays hyperopic defocus. But peripheral refraction itself is always quite myopic in its defocus. Anyway, interesting vision thing. Somebody, one of you guys, optometry type people, can explain why that looks like that. Alright, what's the first thing we do? We want to find our pooled standard deviation because we want to compute effect size and confidence intervals. And for that, we need to start with a standard deviation. Standard deviation for that is the square root, we can see here the square root of this estimate. Now, I had to run a frequency table, as we saw, to get the n's, because the n is going to change, and here it is. Here's the results from the frequency table, minus 4 to 3. These are the number of people at each of those categories. I've pasted that into here, because when we look at the standard error, remember the standard error is the standard deviation divided by the square root of n. And because the n are different each place, we need to calculate all the standard errors separately. It's a different standard error for each one. Now, we're going to compute two confidence intervals, 84% and 95%. In papers, you see 95% confidence intervals. But I like 84% intervals because, number one, they give some sense of precision of the mean, and two, if they don't overlap, the means are significantly different. If they do overlap, they're not. The 95% confidence interval is too conservative. It will overlap when things are significantly different. And if you plot the mean plus or minus 1 standard error, that's a 68% confidence interval, and that's too liberal. It will not overlap when the differences are in fact not significant. So the 84% is just right, and that's the one I like to use. So to do that, we have a t-inverse and use the t-inverse function, and 84 is the p-value that we stick in here. It asks for the probability, and that's going to be 1 minus 0.84 or 0.16. And then the degrees of freedom are the n, 105, minus 1. And that gives us a t of 1.415. And the confidence interval is basically the t times the standard error. And it's the same thing with a 95%, except now it's 0.95, 1 minus 0.95 gives us 0.05. The degrees of freedom are still the same, and that gives us a 1.983. So you can see we're multiplying to get the confidence interval, the 95% confidence interval. It's bigger than the 84% confidence interval because the t is bigger. So that's how we calculate confidence intervals. And the thing that you need to know about confidence intervals is, what is the usefulness of the confidence interval? Well, number one, it measures the precision of your estimate. So the narrower the confidence interval is, the more likely you are that you're overlapping the true underlying mean. We get this mean, minus 0.21 diopters, but that's not the truth. That's a sample from the truth. And the confidence interval, if we were to do this study again, we would get a different confidence interval with different limits. And the percentage of the confidence interval, 84 and 95, says that in the long run, the confidence interval that you compute will overlap the true mean at that percentage. So it doesn't mean that the truth falls between plus or minus 0.104 or plus or minus 0.074. It means that this will overlap the truth 84 or 95% of the time. It's a subtle distinction, but one that's important in the sense that you don't want to mislead yourself. We talked about the p-value in the last video. The p-value is an index of how compatible the data are with the null hypothesis. By itself, it doesn't tell you anything. It doesn't tell you much. when you add the confidence interval to these estimates, it gives you a pretty good idea of where the truth lies, in the sense that these confidence intervals will overlap it. But this graph is not a graph of the truth, it's a graph of one sample. It was a big sample, but it's still a sample subject to random error. Now the other thing we want to know is, we see these guys are different, but how different are they? What's the magnitude of that effect? And to do that, we use effect size. And effect size is the difference between means divided by the standard deviation. So if we wanted to test -4 compared to 0, we would take minus 0.21 subtracted from 0.39, which would be minus 0.6 divided by 53, and we would get a standard deviation that's about 1.1 or something. Now I have done that down here this is the pairwise comparisons table. And I'm interested in the zeros, so I have 0 compared to -4, -3. Now, you could do an equals and then parenthesis for from the estimates 4 minus 0, but this right here, this column right here, is the mean differences. So the mean differences of those two numbers. So the computer's already done this for you, and I just take advantage of having already calculated. Remember we said it was about 0.6, well there's 0.597. That was pretty close. So, and we said it was a little over 1, so it's 1.112. This is the standard, the effect size. And you can see it's the difference between the means divided by the standard deviation. And we do that for each of the years, and we see that we're at over a standard deviation for years between 0. So the I is that growth compared to 0. It's these two compared to this one. That's real different, a standard deviation apart. And 0.8, 0.5, and then the effect size drops down to not too much, and it is not so significant. You can see here it's 0.34. It says our difference is 0.108, so we would suspect that 0, the estimate of 0 at 0.39 and 0.21 overlap. So, or no, they're slightly different. So if we look at this 0, you can see it's close but not overlapping. So the p-value is small because it's close, but it is significant. Alright, so we have effect size and confidence interval always to be reported in conjunction with the p-value. You should never create a table that just gives the means with a p-value and talk in your discussion about how those two are significantly different. You need to add the effect size, and you need to tell the people how precise you are, either with the 95% confidence interval in the text or the 84% confidence interval in the graph. Either one, I'm going to say, is okay. They both give you an idea of your precision. Alright, and these tables are just basically, everything is done the same way, and you do it, and it's pretty interesting. So that's it. Thank you.